So we are in causal inference and statistics, that book right there, and we are in the last chapter. And the last chapter deals with counterfactuals, and I think maybe because there's a lot of applications to counterfactuals, that may be a little bit math heavy. The book kind of relies in the last bits on just kind of demonstrating some of the things that you can do with counterfactuals without really developed discussion. And so I guess in order to supplement that, I wanted to go through the examples as well as the questions, right? So we've been doing the questions, but I wanted to go through some of the examples as well. And so that's what we'll do here. Okay, so here's the first example, example 4.4.1, which starts on page 107 in the book. And you can read it for yourself, but roughly what's going on is that there is a government program that trains people looking for jobs, and with the hope of helping to get them hired somewhere. And there was a randomized experiment with this program that demonstrated that people that received training were more likely to be hired than people that did not receive the training. And so there you go. And so the program is funded. Okay. But there's critics, and they are pointing something out, or a possible concern, which is that that in the real world, what's happening is people are, self-enrolling into the program, and those people may be a unique group of people, such that they would find jobs anyway without the training, right? And so there may be something of a selection bias taking place here. Now, there is another thing that kind of casts a cloud over the entire example here, but we're just going to ignore it. But that is that, in the real world, in this randomized study, people had to agree to go into the study, and the people that agreed to go into the study, may themselves be, not typical. So if the critics' concern is that there is kind of a selection bias taking place in the real world, there's also a selection bias taking place in the randomized study, which I think could be marshaled to further argue against the program. But we're going to ignore that, I guess. So we're kind of asked to try to determine who is correct. Is the program actually beneficial, or is it just, or are the results of it just simply a function of selection bias? Okay. So the first thing that I do here is to just try to think about, what could be happening and try to represent those possible beliefs in terms of these DAGs here. And so it could be that that training and aptitude are affecting whether or not somebody gets hired or not, but aptitude and training aren't, affected. It could be that those with the high aptitude are more likely to receive or to opt into training or be hired. It could be that those with it could be the same thing, but training still helps. So regardless of somebody's aptitude, training still helps. Okay. So roughly what the believers in the program believe is that this arrow between trained and hired exists. It's a non-zero value, but the critics think that that arrow might be zero. Okay. So we're going to go through some, I guess, math here, but I want to point out that, I think that you could actually reason yourself to the correct answer here without doing any math. Okay, why? Well, because if this really represented a randomized experiment, well then, the group that received training, some of those people would have been, the people that, some of the people in the trained group in the study would be representative of the people that would self-opt in to the program anyway. And the randomized experiment showed that there was, that this arrow existed, that it was some positive value, that training, improves somebody's chances of being hired. And so I guess kind of peeking behind the curtain here, because we could because we had an experiment that could close this back door here, because we had an experiment that could close this back door here, that already enabled us to determine the effect of training on, somebody being hired, and so we don't have to go through the whole rigmarole. But we'll go through the rigmarole, I guess, anyway. So, all right. So what we're being asked to find here is the effect of training in the trained, okay, or treatment in the treated. But training also works for T, so I'm going to use that. And so that's just, again, the formula that we're probably hopefully familiar with, right? So it's the expected value of being hired given T equals 1 with the counterfactual being hired when T equals 1, given that T equals 1, okay, minus the expected value of the counterfactual of H when T equals 0, given that T equals 1. Okay. So now, what's interesting about these counterfactuals is that while we do have data on this first one here, right? We already know the value of H when T equals 1, given T equals 1, right? That's just the effect of, or that's just the expected value of H given T equals 1, and we get there by the consistency rule that's presented earlier in the chapter. But we don't have data on this guy here, right? We don't know the counterfactual for H when T equals 0 in the subset of the population for whom T equaled 1, right? We don't, by definition, we don't have that data, right? Because if we are only looking at people where T equals 1, we don't know what their value would have been if T equaled 0. So we're going to see if we can find some expression here that somehow gets rid of this discrepancy between the counterfactual scenario and the observed data. So if we could model this, which I'm claiming that we can, then we have a chance here. So if this was all linear functions, and that's what we're going to assume, then we could just go through trying to find this value here. Okay. I'm sorry, this value where T equals, the counterfactual is T equals 0. So let's actually we're going to do both. But so I already said that this value comes out to equaling this without the counterfactual, but we want to get it in terms of our model. Okay. So here we have that the expected value of H is this guy, right? So it's aptitude plus its coefficient, training and its coefficient plus the error. Okay. And I'm not going to go through step by step here because I've done that in question 4.3.2c. And so watch that, but roughly speaking, we view this counterfactual as an operator that just pushes into the parentheses, identifies anywhere where there's a T, and then makes that thing equal to whatever we're setting T equal to. Okay, and we go through all of that. Okay, and then whenever we need to find a coefficient, right? So in this case, we're trying to find B. Well, then we can just use this expression for that coefficient. Okay, but like I said, I'm not going to go through the entire process here. So watch the video on 4.3.2c to kind of see how we might work through that. But I think all the steps here are correct. And then we do the same thing for counterfactual where T equals 0. Okay, and so our expression for the ETT breaks down into this, and if you notice that the only difference between the two is B here. Okay, so the expected value of training and the trained is B. Okay, well, I realize that I kind of skipped a step, but what is B? Well, B is the effect of training, right? Well, what is that? That is just this arrow right here. Okay, and that's what we found in the randomized experiment. Okay, so in other words, because we had this randomized experiment where we could close the back door, we were able to estimate the effective training in the trained, and it's, in this case, B. And like I said at the beginning, we probably could have reasoned ourselves there without going through all of the math, right? Just because we knew that we had a randomized trial, we could close the back door, and therefore we already have an estimate of training, okay, or the effective training. And so what this entire example is trying to get us to do, and then we will further explore in question 4.41, is to just understand the connection between having access to a back door that we can close if we wish, and then also being able to find a counterfactual. And so if you remember from way back in the book, you know, in order to do these backdoor closings, we had the backdoor adjustment formula. I'm not really sure where that is, but I'm sure if you scroll up and down or just run a search into the Colab sheet, you'll find it. But for counterfactuals, we have a slightly modified version, which adapted to this problem looks like this. Okay. Just a couple of things to notice about this modified backdoor formula is that in the non-modified backdoor adjustment, you know, we are, you know, if we're trying to control for A here, aptitude, then we would just, you know, we would multiply everything by the probability of A. But now we are multiplying by the probability of A given the observed value of, in this case, T. Okay? And then also we were looking for the probability of our outcome here, H, where T is set to the counterfactual value. Okay, we'll call that good.